Okay, so let's get started. Welcome to the first session of Friday. It should be a small mistake that I'm introducing my co-author, but anyways, our first speaker will be Sisi Zhou. She will be talking about quantum error correction meets continuous symmetries, fundamental trade-offs, and case studies. Please.
Hi everyone. Today I'm going to talk about the fundamental trade-offs between quantum error correction and continuous symmetries. So, first we all know that quantum noise is one of the biggest enemies of building a real-life quantum computer. And quantum error correction is an important tool to protect quantum information from noise. And it works in such a way that a bunch of logical qubits are encoded in a large number of physical qubits. So for example, we can take a look at this 9-qubit shortcode here. One logical qubit is encoded into 9 physical qubits. And the decoding channel works in such a way that for any noise acting on this encoding channel, the effect of noise can be completely erased, which means that if the input state is psi in the logical qubit, then the output state should also be psi. So if we take a look at this in the abstract version, we can take a look at this diagram. So suppose we have an arbitrary logical qubit state or any logical state psi. And our goal in quantum error correction is to perform this identity operation on this logical qubit. Then what's happening is that we first do an encoding operation, and there is a certain noise channel we want to correct. And then there's a decoding channel such that the entire error-corrected noise channel is equivalent to the identity channel in logical space. So it works very well if we want to know if we want to build a quantum memory. However, if we want to perform useful quantum computing, we also need to perform arbitrary type of quantum gates on this quantum state. So for example, here we can take a look at the situation where we want to perform a logical gate UL on an arbitrary state psi. And then since we are doing quantum error correction as well, what's going on here is that we must design a physical gate that's acting on the physical qubit such that when it is sandwiched by the encoding and decoding channel, the entire channel gives us the logical unitary operation UL. So we can see from these two diagrams here that if we want to perform non-trivial logical gate operation on psi, then the structure of noise and the structure of the physical gate must be fundamentally different from each other. So this is actually a key observation leading to the proof of Easton-Continual theorem. So Easton-Continual theorem is a no-go theorem stating that any quantum code that can correct local errors does not have a set of transversal logical gates, which is universal. So here by transversal, I basically mean the situation where we have like a M-partite system, and then the gate acts independently on each of the subsystems. So the entire gate is the tensor product of unitary acting on each subsystem. And we call this type of gate transversal gate, which is very useful in fault-tolerant quantum computing. So in order to prove the Easton-Continual theorem, we first know that there's this quantum error correction condition, which tells us that given a error correcting code, which type of noise can be corrected. So it actually states that if P is the projector onto the code subspace, then Ki dagger Kj has to act trivially in the code subspace. So Ki here is basically the cross operator of the noise channel, and I could indicate like the index for different type of noise. And from this quantum error correction condition, we can see that if an error correcting code can correct local error, then for any local operator E, it must also act trivially in the code subspace. And then that means if we consider a type of gate which have this form, so we assume that this type of gate is a logical gate, and it is given by this form where we have a local Hamiltonian in the exponent of this operator. Then from the quantum error correction condition, we can see that this type of gate must also act as the identity operator in the code subspace, because the generator of this is going to be trivial, satisfying this condition. So as a result, we basically prove that any type of gate that can be written as this form, which is also logical gates, must act trivially in the code subspace. So theta here is basically can be some real number in the neighborhood of 0, and this type of gate actually forms a connected component of the identity in the entire group of transversal logical gates from the group theory perspective. So in that case, basically, if this connected component acts as identity, as we've proven using the quantum error correction conditions, one can also prove that the type of gates can be performed using transversal logical gates must be finite and therefore cannot be universal. So in our work, we went beyond the scheme of quantum computing. Actually, we consider the general trade-off between quantum error correction and continuous symmetries. So basically, we are trying to ask the question if there exists a quantum error correcting code that respects continuous symmetry in the system. So by continuous symmetry, I basically mean the situation where the gate commute with this symmetry of the encoding channel commute with this symmetry operation. So here G is a continuous group, and UL and US are different representation of this group in the logical system and the physical system. And we would say a code is covariant code if it respects this type of symmetry transformation. And the question is, can a code simultaneously be a good error correcting code and also respects non-trivial symmetry operation? And we will see that there is certain conflicts between these two concepts. And we will also derive trade-off relations between the degree of good error correcting code and the degree of symmetry property of the quantum code. So okay, so now let's take a look at the exact setting of our problem. So again, by quantum error correcting code, I basically mean the situation where, given the encoding channel and the noise channel, there exists a recovery channel such that the entire error corrected noise channel would be equivalent to the identity operation in the logical space. And I would use Ki to denote the cross operator of this noise channel. And I'm going to consider U1 symmetry group in this work. And so I'm going to consider the code that respects U1 symmetry, which is called U1 covariant code. And it describes the case where the logical Hamiltonian evolution generated by HL is equivalent to the physical Hamiltonian evolution generated by HS, while theta is just an arbitrary real number. So again, we have this quantum error correction condition to help us determine if the code can correct certain type of noise. And combining these two, we can see that if the physical Hamiltonian is inside the span of Ki dagger Kj, then HL must act as identity in the logical space if the code is simultaneously error correcting and covariant. So however, we don't want a trivial symmetry operation on the logical space. So if we assume that HL acts non-trivially in the code subspace, then this condition must be violated. So basically, this condition, which we call Hamiltonian in crossband condition, is a necessary, is a sufficient condition for help us to determine the non-existence of exact error correcting and covariant code. And I also want to remark here, by Hamiltonian, I do not mean the Hamiltonian of the entire physical system. I just mean the charge operator of this U1 group in the physical space. Okay, so we will assume that the HKS condition is satisfied throughout this talk. And it is actually a quite general condition. For example, if you consider the case where K is local operator and the Hamiltonian is also local, then it definitely satisfies this HKS condition. And since we cannot simultaneously have good error correcting code and exact covariant code, we are going to consider the approximate case. So we will use two different parameter, epsilon and delta, to quantify the degree of error correction and the degree of U1 covariance. So basically, epsilon is going to be the distance between this error correcting noisy channel and the identity operation. And in particular, we will use a purified distance, and we are going to minimize the distance over all possible decoding channel to find the optimal decoding channel. And there are actually three types of way to define delta. The first one is called global covariance, which is basically the case where we maximize the distance measure over the entire group, which means we maximize it over all theta. And we could also consider local covariance violation, which basically means that we need to consider the derivative of this distance measure with respect to theta. And one could even consider like the charge conservation, which means which is kind of the difference between the input charge and output charge given a quantum state. So, and in fact, for the sake of time, I'm going to only focus on this global covariance violation in this talk, while the result on other type of definition is contained in our paper. So our main result is that we derive various trade-off relations between quantum error correction and symmetry. So here are the two types of trade-off relation I'm going to focus on. So the inequalities looks complicated, but basically from this expression, we can directly see that it demonstrates the robustness of the incompatibility between error correction and symmetry. So if epsilon is sufficiently small, delta is going to be lower bounded by a positive constant and vice versa. So it means that if you have a error correcting code with a very good property, then you cannot have an exact covariant code, have it as an exact covariant code. So I'm also going to explain the parameters appearing in this inequality a little bit. So delta HL and delta HS basically means the strength of the Hamiltonians, and it is the difference between the maximum and minimum eigenvalue of H. And the J here is actually a complicated expression, but it is related to the saturation of the HKS condition. And F here is actually the quantum Fisher information of this quantum channel with respect to theta. So we're also going to provide code examples that nearly attains the bound in some scenarios, providing evidence that our bound is going to be tight. And I also want to remark here that there are many previous work focusing on the case of the exact covariant code, basically the situation where delta is equal to 0. And we managed to generalize this, resulting to the general trade-off between epsilon and delta. So first, let's take a look at the behavior of these trade-off relations. And as I mentioned, the entire setting of this inequality based on the structure of noise. So we are going to consider different type of noise and different type of Hamiltonian. So we are going to consider first the situation where the system, again, is a n-partite system, and each subsystem is denoted by Si. And then we assume that the Hamiltonian is basically the tensor product of each Hamiltonian evolution on each system. Basically, it's kind of like a transversal gate. And we assume the noise is a random local noise. Basically, it describes the situation where a noise acts on only one of the subsystems, but which is chosen uniformly at random. So in that case, one can try to get the scaling of these parameters with respect to the number of subsystems. So you can sort of verify that J is going to scale linearly with respect to N, and also delta HS is going to scale linearly, and F is going to scale quadratically with respect to M. So then we can see that for sufficiently small delta, epsilon is going to be lower bounded by the scaling of 1 over n. And for sufficiently small epsilon, delta is going to be lower bounded by 1 over the square root of n from the first type trade-off relations and 1 over n from the second type. So basically, we see that the first type of trade-off relation will give us a tighter bound when we consider this random local noise. And another type of noise that is important is called RID noise. It is sort of a stronger noise compared to the random local noise. So it describes the case where noise acts on every subsystem with a fixed probability, but but it acts basically on the entire system. So it's sort of like more stronger than the random local noise because noise does not act on only one of the subsystems. So in that case, one can verify that the scaling of J and delta HS does not change, but the scaling of F is going to decrease to the linear scaling with respect to N. So in that case, we can see that the lower bound of epsilon is going to be given by 1 over the square root of n from the second type of trade-off relation. And the scaling of delta, the lower bound of delta for sufficiently small epsilon is going to be 1 over the square root of n, which is the same as before. But in this situation, we see that the second type of trade-off relation gives us a better result in terms of the lower bound on epsilon, the QEC inaccuracy. So okay, so now I'm going to talk about one application of our results, which is to provide limitation on transversal logical gate. So recall that we've shown that if we consider this random local noise on one of the subsystem, we would have a lower bound on delta, which is given by 1 over the square root of n. So if we have an exact quantum error code that has distance at least up to 2, then this situation, this lower bound on delta must hold because epsilon would be 0 in that case. And furthermore, we assume that there's this transversal logical gate acting on the quantum error code, which have this form. So D is kind of representing the precision of this rotation of HL. So the larger D is, the higher the precision of this HL rotation is. And we can see that if we take D to be like very large, we would have approximately an covariant code because 1 over D is going to be a very small number, and it becomes almost like a continuous application of this gate. So in fact, then one can basically prove that there is a relation between delta and D, which says that the delta times D must be upper bounded by the scaling of n. And combining these two, we can prove that D is upper bounded by the scaling of n to the 3 over 2. So it's basically provide an upper bound on the precision of this transversal logical gate. So as an example, if we consider a stabilizer code, it basically means that the gate cannot, this type of transversal logical gate cannot go beyond O of log n's level in the Clifford hierarchy. So basically it shows that by considering this approximate symmetry property of error code, it is possible to get a bound on the gate precision using our results. So now I'm going to provide 2 examples of error code that nearly saturate our bound. So the first type of code is an exact error code, and it is called quantum read-Muller code. So the quantum read-Muller code is actually, I'm going to consider this 2-dimensional, which means like we have only one logical qubit, quantum read-Muller code, and the code word is going to be given by the superposition of computational basis, which is described by this classical shortened read-Muller code. So for example, here we write down the truth table of all degree 1 Boolean function. And if the first digit is 0, it gives us the computational basis for a logical 0 state. And if the first digit is 1, it gives us the basis for the logical 1 state. So this type of code have a very nice property, is that it have this transversal logical gates looking like this. So basically, if we want to implement the rotation of the Pauli Z operator, we can we can do this up to this certain precision where T can be very large. In that case, we would have an approximately covariant code. So we can compute delta in this case, which is going to be 2 over the square root of n. And it exactly match our lower bound up to a constant factor of 2. So the second example is called modified thermodynamic code, and it is actually a family of codes that interpolate between exact covariant code and exact error correcting code. So in the exact covariance end, basically when we take this parameter Q to be 0, we would have this exact thermodynamic code. And it is actually given by the decay state of a spin chain. So basically, if we consider this n spin chain and use this charge operator as the sum of Pauli Z operator, the decay state is basically the symmetric state, which is the energy eigenstate of this charge. So one can verify that if the state is a decay state, it is actually naturally going to be a covariant code, but it cannot be an exact error correcting code. And we could add this extra term here based on parameter Q, and we can verify that when Q is equal to 1, then the error correction condition is satisfied and the code becomes exact error correcting code. So one can calculate epsilon and delta in this case, and epsilon is going to scale like 1 over n, which exactly matches the scaling of our lower bound. And similarly, the scaling of delta is going to be the same as our lower bound. Okay, so finally, I'm going to talk about the proof technique of our two trade-off relations. So in fact, the techniques to prove the two trade-off relations are very different. So in order to prove the first type of trade-off relations, we make use of this concept called charge fluctuation. It is sort of an indicator of whether the code is an exact error correcting code and exact covariance code. So charge fluctuation is defined by this expression here. So it's basically the fluctuation of charge in the logical subspace. And when epsilon is 0, that means when the code is exact error correcting, one can use the quantum error correction condition to prove that chi has to be 0 if the code is exact error correcting. So it's this end. And when delta is 0, that means the code is exact covariant. And one can also prove that chi has to be delta HL, which is positive, because this physical Hamiltonian must be mapped to the logical Hamiltonian if the code is exactly covariant. So we can see that it is somehow an indicator of the incompatibility between the error correcting property and the covariance. So in order to get our trade-off relations, we first try to put a lower bound on delta using the distance between delta HL and chi. And we can also put a lower bound on epsilon using the distance between chi and 0, which is basically the absolute value of chi. So combining these two, we will be able to prove that prove this first type of trade-off relation. Okay, so this is the first proof technique, and the second proof technique make use of a different concept called gate implementation error. So we actually consider the distance between these two gates on the left-hand side and right-hand side. So on the left-hand side, we have a quantum channel, which is the composition of 4 quantum channels: the encoding channel, the physical Hamiltonian evolution, the noise channel, and the decoding channel. And we can see that if the code is covariant and also perfectly error correcting code, then it's going to be equal to the logical Hamiltonian evolution on the right-hand side here. However, if the code is not exactly error correcting and covariant, gamma is going to be larger than 0. So basically one can show that the sum of epsilon and delta is going to be lower bounded by gamma. And if it is possible to derive a lower bound on gamma, we would have our second type of trade-off relation. So in fact, you can find this lower bound on gamma using method from quantum metrology. And basically, you can sort of calculate the Fisher information of this quantum channel, and you can show that it's lower bounded by the scaling of 1 over gamma square, and then it effectively put a lower bound on gamma. And combining these two, we would have this trade-off relation between epsilon and delta as our second result. So okay, so to summarize, we've derived several type of trade-off relations between quantum error correction and continuous symmetries. And we also show that the relations are nearly optimal in certain scenarios. And we also provide application of our results in fault-tolerant quantum computing. And there are also other type of trade-off relations based on different symmetry measures that I didn't have time to discuss. And there's also a detailed proof technique based on metrology and resource theory that is contained in our paper. Finally, there is also the potential physical applications of our results in quantum gravity and many-body physics and so on, which is also discussed in our paper. That's all for my talk. Thank you very much for listening.
Okay, thanks for the nice talk. We have some time for questions.
Sorry, one question. So, in this talk, you consider continuous operation. So I'm slightly confused, but usually in the quantum computation, we only use some discrete parameters, the discrete operation. So why you consider continuous operation?
Yeah, so so actually the motivation of considering the continuous symmetry does not exactly rooted in quantum computing, because it's actually very important in a specific physical system that respects certain symmetry. So if the dynamic that generates the error correcting code respect the symmetry, for example, if it's like a circuit which is like a charge conserving, then it's going to respect this continuous symmetry. So if there's a charge in the system, it's going to respect this continuous symmetry. But it is of course closely related to this quantum computing case, because in quantum computing case we would also need to apply the logical gates up to a certain precision, and the higher the precision is, the lower the parameter delta is. So basically, if we consider this parameter delta, is also going to tell us a little bit about what's going on in the quantum computing case, but not in the exact way. Yeah.
And also, you consider some hierarchy of quantum operations. I cannot remember, but maybe you show that C1 and C2, C3. So, and C1 is Pauli operation, and C2 is Clifford, and C3 is maybe set of quantum gate. So you consider that kind of hierarchy. So I cannot remember where it is.
I didn't exactly got the question. Can you like repeat it again? Yeah.
You show somehow hierarchy of quantum operations. I cannot remember where it is.
Clifford hierarchy, page 11.
Hierarchy, yes, hierarchy. So, well, I could not understand why you consider that hierarchy, and I could not understand the role of that hierarchy in that context.
Yeah, so I guess it's because like many known example of transversal logical gate have this form. So so that's why it is important to consider like this type of transversal logical gate where basically you put this H to be a constant, and then you consider a family of code where D increases. So so D would increases with the number of qubits. So then in that case, it is closely related to the Clifford hierarchy if you consider stabilized code, because basically the larger D is the higher the Clifford hierarchy you are in. So
Yes, limitation transversal logical state. So in the slide you consider, yes, this. So your method works with that kind of a higher hierarchy. And that VL. Okay.
Yeah, so basically one example is this quantum ring code. And you can see that basically you are in each level of Clifford hierarchy. If you can implement this, okay, yeah.
Okay.
Yeah. I also have some comments that I make, but maybe let's take it offline because we already past time.
Okay, I'm fine.
Okay, let's thank the speaker again. So our next speaker